welcome to the course Nature and Properties of Materials. In week 7 we'll talk about material selection in engineering design. So this course is offered by Professor Vishak Bhattacharya, Nature and Properties of Materials, and he's from Department of Mechanical Engineering from IIT Kanpur. I am TA Alka Jangit from IIT Kanpur. So first question is, firstly we'll go through some sample assignment questions, then we'll go through some lecture notes. These both will be helping you in solving your weekly assignments in your exams as well. So first question is, select the material for a circular cross section cantilever beam loaded at its end having high strength and light weight. And your options are sigma square upon E rho or under root E divided by rho or sigma to the power 2 by 3 divided by rho or sigma to the power 1 by 3 divided by rho. So out of these you have to find out which of these will be the material property index. Okay, so select the material for a circular cross section cantilever beam loaded at its end having high strength and light weight. Okay, so correct answer will be sigma to the power 2 by 3 divided by rho. So in case of when we are trying to find light weight, so we'll take mass as a consideration. So mass can be given as m equals to rho. Rho is your density times the volume, and volume for the circular beam can be given by pi d square L upon 4. So it can be further written in terms of stress and force and length, so keeping all other properties same, but the equation of d square is written in terms of force and length and sigma. So it is written as 32 FL divided by pi sigma times 2 by 3. Okay, then further we segregate these constants at one edge, and geometric parameters such as length, width, thickness, those are segregated at one place, and functional parameters such as force, pressure and others, they are segregated. And then finally material property, which will totally depend on by changing material. Okay, so in this case you will be having such as density, the strength of material or fatigue strength or other properties. So in this case you want to minimize the mass, so you will be minimizing this material property index. So you have to take inverse of this, and it is also known as performance index. So you have to maximize the performance index. So performance index is given as 1 upon material property index. Okay, so material property index is given as rho upon sigma to the power 2 by 3. So you have to minimize this and maximize sigma to the power 2 by 3 divided by rho. Okay, so this is your performance index. So you can be asked performance index for this particular case as well. Okay, so there are around 4 to 5 case studies that are given in this particular lecture. So you have to at least remember or try to remember these particular equations and try to figure out what are the material property indexes for various case studies. Okay, now in this case there will be a line corresponding to this performance index, and below this line you will be having materials which don't fit the criteria, and materials which are above this, these will be falling in search region. So for selecting a cantilever beam you will be selecting materials which are falling in this range. So these various ceramics and CFRP, these are the ones that you can select. Next question is second. So next question is, which element is most abundant in the atmosphere? So atmosphere is the one that is surrounding us, consisting of various gases such as nitrogen, oxygen, argon, carbon dioxide, sulfur dioxide and others. So out of these, which gas is the most abundant? So your options are nitrogen, aluminum, silicon and oxygen. So out of these, aluminum and silicon are the ones that are not even gases, so they can't be in atmosphere. So your options will be between nitrogen and oxygen. So in nitrogen, in case of our atmosphere at Earth, we have nitrogen as the highest percentage. Okay, second highest is the oxygen. So nitrogen is the most abundant in the atmosphere, and oxygen is the most abundant element in Earth's crust and oceans. So in oceans also you find hydrogen oxide. So oxygen has higher molecular weight. So comparing the weight percentage and volume percentage, oxygen will be more compared to hydrogen even. Okay, so in oceans also, here you can see oxygen is the highest, 85 weight percent, and then hydrogen is 10 weight percent. Then chlorine, because of NaCl part, and in NaCl also Cl is heavier. Then you have sodium, second NaCl is higher in oceans. Then you have magnesium, sulfur, calcium, potassium, bromine and carbon. In case of crust, so earth crust, we have highest amount is in terms of oxides. So oxygen is highest. Then you have silicon. So silicon oxide is very silicon oxide and aluminum oxide and some silicates and some other complex aluminum compounds are found in the soil. So these form the highest amount, and aluminum bauxite ore is also very widely available. So then aluminum, and after that you have ferrum oxide and ferric oxide, which is abundant. Then you have calcium, sodium, potassium, magnesium, titanium, hydrogen, phosphorus, manganese, and fluorine, barium, strontium, sulfur, carbon in this particular order. Then we also have, in case of atmosphere, we have elements. Nitrogen as the highest, 79 weight percent. Oxygen second highest as 19 weight percent. Argon as 2 weight percent, and carbon dioxide as 0.04%. Next question is, which of the following strategy cannot be used to encounter the shortage of materials? Your options are batch production, continuous type of product, or effective. Okay, so which of the following strategy cannot be used to encounter the shortage of materials? Your options are batch production, continuous type of product, effective utilization of machine, or all of the above. So out of these, only one that cannot be used is batch production. Okay, so batch production is a method of manufacturing where the products are made as specified groups or amounts within a time frame, and a batch can go through a series of steps in a large manufacturing process to make the final desired product. And continuous type of product and effective utilization of machine helps against shortage of materials. So these two methods help against the shortage of materials, while batch production doesn't help. Next question is, for a constant growth rate of 5%, what will be the doubling time, TD. So doubling time is in how much time your product production will double in size. So your options are 13, 14, 15 and 16. So you just need to remember the formula for the doubling time, and you just need to put the value of R from growth rate 5. So it is basically just 70 upon R. So how this equation comes about? So for a constant growth rate of R%, the formula for the doubling time TD is given by TD equals to ln2 upon growth rate. So it can be further written as log 2 upon log 1 plus R upon 100. So it can be solved and written as 70 upon R. So here it can be approximated as 70 upon R. So 70 upon R, so R is given as 5. So 70 upon 5 will be 14. So 14 will be the correct answer. Next question is, which material is less recyclable and eco-friendly? Your options are metal, polymers, ceramic, composites. So as from the news as well, you can know that polymers are becoming problematic in terms of their disposal as well as their recyclability. So these are not very easy to dispose. So they don't degrade with time, and so there are a lot of efforts into making biodegradable polymers as well, so that they don't affect our environment in bad way. So polymers is the correct option. So polymers consist of long chains of carbon and hydrogen atoms. These molecules form an interatomic type of bonding and is adamant, meaning it is tough for microbes to break the bonds and digest them. Thus a long period is required to decompose them, and the polymers with hydrolyzable backbones are susceptible to biodegradation under particular conditions. Next question is, which diagram is associated with natural resource recovery? Your options are HP, McKelvey, bubble chart or 2D chart. So correct option will be McKelvey type of diagrams. So here this diagram is shown. So in case of a McKelvey diagram or McKelvey box, it is a visual representation used to describe a natural resource such as a mineral or fossil fuel based on the geologic certainty of its presence and its economic potential for recovery. The diagram is used to estimate the uncertainty and risk associated with the availability of a natural resource. As a geological assurance of a resource's occurrence decreases, risk will increase. And also as the economic recoverability of a resource decreases, so if you can't recover it in economic way with less amount of money, then also risk will increase. So here you can see there are various types of resources: conditional resources, reserves, identified resources. So identified resources are easy to use, but the ones undiscovered resources in non-districts, in undiscovered districts, then speculative type of resources, hypothetical resources, these are the ones that require much more resources into extracting. So degree of certainty of existence are for these type of resources, and feasibility of economic recovery will be keep on increasing in this direction. So here these are the classification of mineral resources used in this volume. seventh question is for increasing factor of safety blank. So if you want to increase the factor of safety of certain appliance or some machinery, what can be done? So your options are diameter or thickness is reduced, impurities are added. So if you're adding some impurities, it's more likely to fail earlier. So sometimes your impurities can act as inclusions, so these will initiate cracks rather than providing them higher strength. Okay, and other option is diameter and thickness increases uh, or the heavy material is used. So if you want to increase the factor of safety, you will have to increase the diameter and thickness of that cross section of that particular appliance. For example, if you are using any cantilever beam, all those case studies that you have studied in this week's lectures, so if you increase the diameter, then it will provide you with the higher strength. It can resist the failure more compared to the lower dimensions. Okay, so heavy material is used. So heavy material usage will also come with the other disadvantages. Impurity is also not correct, and diameter thickness reduction will lead to adverse effect on the factor of safety. Okay, so third one is the correct option. So for increasing the factor of safety, the thickness or diameter of the material is increased, leading to the use of more material than required. But as you are increasing the material used, but if it's failing and at the higher timeline, then also you will require less number of changes in that particular appliance. So it is you have to compromise with one of these things, so material usage or the factor of safety. Next question is, which material is not used for making light high performance connecting rod? So connecting rods need to be having good fatigue resistance, and some of the options that are given are the magnesium alloys, titanium alloys, aluminum alloy and zinc alloys. So all these are some of the light materials, and these should all are ductile except zinc alloys. So zinc alloy manufacturing is also so not easy to process. Zinc alloys and zinc and its alloys are not easy to process, and these are not ductile and they are not tough, so these are not used for making connecting rods. The materials that are used for high performance connecting rods, these are, first is magnesium alloy. So in this case you have AZ61 and related alloys which offer good all around performance. Next is titanium alloys. So Ti64, which consists of vanadium, is the best choice for high F upon L square. So F is force and L is length. So these are your parameters. If you're considering higher forces, then you choose titanium alloys. Next is beryllium alloys. So the ultimate choice, but it is difficult to process and very expensive. Aluminum alloys, these are cheaper compared to titanium or magnesium, but they provide lower performance. Next question is, which materials are abundantly available? Your options are copper, mercury, silver, gold, aluminum, iron, or tin, tungsten. So out of these, third one would be the correct option. So as I told earlier also, in earth crust you have abundant amount of silicon, aluminum and iron. These three elements are abundant along with oxygen. So explanation is given here. So copper, silver, tungsten, tin and mercury are rarely available, and iron and aluminum are the most widely available materials due to their abundant ores, and also these are very easy to recycle as well. Aluminum is highly recyclable material as it forms a protective oxide layer and it doesn't undergo a lot of oxidation or corrosion along its lifetime. So after even fracture, you can use that particular material in recycling, and then you can make new appliances with that particular aluminum. Iron, on the other hand, it undergoes corrosion, but when you manufacture steels, stainless steels, then it also provides good corrosion properties, and then also it can be used in recycling a lot compared to some other materials. Next question is, for a household fan, which of the following mechanical properties is most important? So your options are creep resistance, fatigue strength, seawater corrosion resistance, or oxidation resistance. So as you know, you are not using your household fan into seawater, or you are not there is always some coatings that are aesthetic coatings are provided on fans, so you don't require much oxidation as well. And creep resistance, so you are using it at lower temperatures, only up to 50 to 60 degrees Celsius in case of India, so you don't require creep resistance as well. Creep, so as I told earlier, creep is the resistance of material to undergo deformation at little bit higher temperatures, up to 0.5 times the melting temperature. So fatigue strength is the only one that is the important property for household fans. So as the fans undergo cyclic type of loading, so it will be most times it fail with the fatigue type of failure. Okay, so it should, your material that you are using for making household fan, it should consist good fatigue resistance. Okay, so for a household fan, the service temperature doesn't increase more than the room temperature, while creep and oxidation resistance properties are required when the temperature increases above 200 degrees Celsius. Seawater corrosion is a chemical property and it is also not required, while fatigue properties are important as cyclic loading is involved in case of household fans. Next question is, which one of the following is not a mechanical property? So your options are creep resistance, density, hardness, fracture toughness. So correct option will be density. Okay, so creep resistance is again, it's related to the mechanical property, so related to dislocations and grain size and grain structure, microstructure. Hardness, its resistance against plastic deformation, again mechanical property. Density is a physical property, and fracture toughness, so it is your material's resistance against fracture. Which material is most widely available? Copper, silver, tungsten or iron? So as I told earlier, in earth crust you have aluminum, silicon and iron in abundant. So iron will be the correct option, and copper, silver, tungsten are rarely available. So these are mostly whichever regions these are found in mines, so these are mostly recycled and used. Next question is, what is Ashby charts plotted between? So your options are two independent properties, two dependent properties, stress and strain, or load and displacement. So stress and strain curve is different compared to your Ashby charts, and HB charts are basically drawn between two independent properties. So it can be plotted such that elastic modulus versus density, or elastic modulus versus endurance limit, or so on. Okay, and next question is, which material is not a good choice for connecting roads? Your options are aluminum alloy, ceramic, titanium alloy, or magnesium alloy. So correct answer will be ceramic. And so in case of connecting roads, it should have good fatigue properties, as I told earlier. So, and also it should be light as well. So in light materials and having good fatigue properties, aluminum alloy, titanium alloy, and magnesium alloys are the ones, and also beryllium alloy, they provide good properties. Ceramic, they undergo catastrophic failure, so they can't be used as connecting roads. Which material is a good choice for cantilever beam for scanning probe microscope? So out of these, elastomer, diamond, lead, and neoprene. So these materials should provide less deflection. In terms of deflection, you will be finding that diamond and silicon nitride, Si3N, and these are the ones that are used mostly for the scanning probe microscope cantilever beams. Now we'll go through some lecture notes. So firstly, material selection in engineering design. So firstly, mechanical design refers to the mechanical components which have mass and they can carry loads, and also they have other functionalities such as thermal and electromagnetic requirements, and these must be manufactured. And the design refers to the selection of engineering materials based on a set of defined properties, and it is a repetitive process. Okay, so this is the flow chart for selecting materials. So firstly, what is the requirement in the market, what is the market need, what is design requirements, then based on that you generate a concept, and in this case you have to determine function structure, you have to seek working principle, you have to evaluate and select various concepts, then embodiment, and this depends on the development of layout, scale and form, then to model and analyze various assemblies, to evaluate and select layouts, then detailing. So then you have to analyze the component in detail, you have to optimize the performance and cost, and you have to finalize the choice of material and process, then you have to find the product specification and iterate, and if it doesn't give the good result, then you have to either go directly up to the concept, you have to restart the process, or you can go one step above as well. Next is selection of properties. So these are various properties which are the parameters for selecting a particular material for any application. First is price and availability. So if you are trying to manufacture a water bottle, then what firstly you'll be finalizing, if you're finalizing material that you're using, so you'll be having various options, and out of those you'll be finding out what is the price, how easily the material is available, and then density and modulus. Then these are the mechanical properties. So density is not a mechanical property. Then you have mechanical properties such as modulus, damping, yield strength, tensile strength, hardness, fracture toughness, fatigue strength, thermal fatigue resistance, and creep strength. So all these properties are considered. Based on various application, you can omit some of the properties, and focus on some properties required in that particular application. Then third is the thermal, optical, magnetic and electrical properties. So for example, if you require formation of some wires, electrical wires, then you'll be focusing on electrical properties rather than optical or magnetic properties. Next is oxidation, corrosion, friction, abrasion and wear resistance. So how much surface finish that is required, these particular properties will also come into consideration. Ease of manufacturing and joining. So some of these steels are easy to join depending on their composition. So those materials are preferred when your material more likely to fracture and it may require some welding, then you choose those type of steels. Appearance and texture and feel, these also come into picture. Next is classes of property affecting product design. So firstly you have economic and environmental properties. So these are the price and availability, recyclability, sustainability and carbon emission. For example, polymers are very cheap but they are not sustainable materials because they are not biodegradable. So you have to keep all things in mind while you are making some product. Mechanical properties, again modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength and damping. Then thermal properties such as thermal conductivity, specific heat, thermal expansion coefficient. In general physical, you have physical properties, density. Electrical and magnetic, you have resistivity, dielectric constant, magnetic permeability. Next you have environmental interaction, which are oxidation, corrosion and wear resistance. Then you have production, such as ease of manufacturing, joining and finishing. Okay, how easily you can join your material, how easily you can finish, surface finish material, how easily it is to manufacture. So some metals such as zinc, aluminum, tin, these have very low melting point, so these are very easy to manufacture compared to other materials such as molybdenum or such as tungsten, which have very high melting point, and other ceramics as well. Ceramics also are not easy to manufacture compared to some metals and polymers. Aesthetic, so color, texture and feel. Now need to determine mechanical properties. So what is the need? So firstly you'll be performing some tensile testing such as stress strain test, which will be giving you some stress strain curves. So based on that you will be analyzing this and you will be getting mechanical properties. So you will be getting fracture strength, you will be getting UTS, you will be getting yield strength, you will be getting elastic modulus, you will be getting ductility. All these properties you can get from these particular data analysis or other types of analysis. Okay, and based on these mechanical properties you can decide how much of the thickness or how much of the diameter you will be requiring in particular appliances. Okay, so you design according to these mechanical properties, and after this design you will be economic analysis and business case. Then you will be if you're using this efficiently, you will be getting some profitable applications. Okay, so you are having raw data, numbers, then you have information, numbers, and you understand. You convert it into information, numbers which you understand, then to knowledge, numbers you know how to use. Next is relative prices. So these are various materials. So as you keep on going downwards, you will be seeing the cost basically mainly reducing. So PVC it is 300, so relative to 100 we have set mild steel at 100, and relative to that we have measured. So cement, coal, these are 20, these are very cheaper. Then you have woods and softwood and concrete at 50, then you have at 90 cast iron, and then you have higher than these fuel oil or the low alloy steels, PVC and plywood. These are higher compared to mild steel. Then in here again you have I think here also we have 100 as steel. So all are about this steel. So here you can see platinum has the highest price, around 12 million. Okay, approximate relative price per ton of the mild steel. So platinum is around 12 million, and diamonds, industrial, these are 10 million, and gold is 9.6 million. Then you have silver, CFRP, and carbon, tungsten carbide cements. All these are also very expensive. And then you go further down, then you will be getting tool steels. These one are relatively cheaper. Epoxy, polyester, glasses, and all. Further down you will be getting lead ingots, some of the metals and some of the polymers. These will be having lower prices compared to these ones. Next is abundance of elements. So I have covered this already. So in this case, in case of earth crust, you have highest of the oxygen. So there are silicon oxides. In silica also you have oxygen, in aluminum oxide, in iron oxide, all these consisting oxides. So oxygen you have in oxide forms. Okay, and then you have second, you have silicon. So silica is mostly found in soil, so silicon is second most abundant, so it is 27 weight percent. Then you have aluminum. Aluminum is found in terms of alumina. Iron oxide is also found, so iron. Then calcium, sodium, potassium, magnesium, titanium, hydrogen, phosphorus, manganese, fluorine, barium, strontium, sulfur and carbon. Next is oceans. So in oceans also you have H2O is the highest amount. So in this case oxygen is heavy, so weight percent will be 85 weight percent, and hydrogen will be second highest, 10 weight percent. Then you have chlorine. NaCl is a lot in case of oceans, so Cl is heavier, so it is 2 weight percent. Sodium is 1 weight percent. Other chlorides can also be present, that's why chlorine is higher. Magnesium, then sulfur, calcium, potassium, bromine and carbon. Then in case of atmosphere, you have nitrogen as the highest, oxygen second highest, argon 2 weight percent, carbon and as CO2 as 0.04. Then the total mass of the crust to a depth of 1 kilometer is 3 times 10 to the power 21 kg, and the mass of oceans is 10 to the power 20 kg, and that of the atmosphere is 5 times 10 to the power 18 kg. So you have to multiply this weight percent to these particular kg. So that much of iron or silicon we have. Doubling time. So it is basically period of time required for a quantity to double in size or value, and when the relative growth rate, not the absolute growth rate, is constant, the quantity undergoes exponential growth and has a constant doubling time or period. Examples include it is applied to population growth, inflation, resource extraction, consumption of fruits, consumption of goods, and compound interest and the volume of tumors. So for a constant growth rate of R%, the formula for the doubling time TD is given by TD 70 upon R. So it is firstly ln 2 upon growth rate, and it can be simplified or approximated as 70 upon R. Next is resource availability. So current reserve is the non-deposits that can be extracted profitably at today's price using today's technology, and the resource base is the equals to current reserve plus known and unknown deposits. So here in this particular McKelvey diagram also you can see, so these are the reserves that we already have or identified ore which is economic to extract. Then at the lower here you have minimum mineable grade. Then if you're moving further down, then you have not economic, which is you need to require improved mining technology to extract these particular ores. Then here in this side you have undiscovered ores, so these are the for increased prospecting, and the resource base which includes reserve. Then in this side you have decreasing degree of economic feasibility, in this side you have decreasing degree of geological certainty. These are the materials and their extraction energy. So energy consumed to extract, so it is gigajoule per ton. So 1 ton of aluminum extraction requires 280 of the gigajoule of the energy. Next is plastic, it is 85 to 180, copper is 140, zinc is 68 and steel is 55, glasses are 20, cement is 7, brick is 4, timber 2.5 to 7, gravel 0.2, oil 44, coal 29. So aluminum and copper, they require electrodeposition type of technique for extraction, so they require higher energy compared to zinc and steel which require melting. Next is availability. So there are two types. So rarely available, in this the elements which fall are copper, silver, tungsten, tin and mercury, and most widely available consist of iron and aluminum which are found in earth crust. Next is steel consumption is doubling in every 20 years, and aluminum consumption is doubling in every 9 years. Polymer is doubling in every 4 years. So as you can also see, as you're moving down further, your doubling time is reducing, and also they are becoming lighter. So we are moving into making our materials into more lighter and lighter. So as in your laptops and your mobiles also you can see, we have moved from aluminum to the polymer side as well. So we are using polymers and some of the composites or aluminum based composites in our vehicles as well, aerospace, aerocrafts as well. So all of these particular applications, they are using more and more lighter materials. Next is how to encounter shortage of materials. So firstly, material efficient design. So it is uses less amount of material. For example, for a good surface property, we can use cheap substrate and good surface finish. So next is substitution. We can substitute rarer materials by more available ones. For example, copper can be substituted by aluminum. So in wires as well, they both have almost very close electrical conductivity, but the cost is different and availability is different. So copper can be substituted with aluminum. Next is recycling. So you can use recyclable material like aluminum. Examples of critical minerals used in advanced technologies. So in solar panels, arsenic, germanium, indium and tellurium. In battery storage, cobalt, graphite, lithium and manganese. In wind turbines, aluminum, rare earth elements, etc. In national defense, chromium, gallium and scandium. In aviation applications, niobium, tantalum and vanadium can be used. Next is eco-efficiency. So it merges ecological and economic goals and improving the productivity of energy and material inputs to reduce resource consumption and cut pollution per unit of output. And it is a win-win approach which benefits both the bottom line and the environment. So in 1989, Procter and Gamble introduced concentrated detergent powders which were called ultra detergents. These took up half the volume of the traditional detergents, and the products cleaned the same amount of clothes but were more convenient for consumers to handle. And these used 30% fewer raw materials and required 30% less packaging, and sustainability cut the energy needed to transport them to market. Next is dimensions, 7 dimensions. So first dimension is to reduce the material intensity of goods and services. So you can reduce the amount of material used in particular application. Next is reducing the energy intensity. So using materials which require less energy for production. And then reducing toxic dispersion. So using materials less, such as which can be toxic to environment. For example, previously lead and mercury type of materials which were used, asbestos and other type of arsenic. The use of these particular elements have been reduced a lot after knowing their particular effects, which can be carcinogenic or which can be very harmful to humans. Next is enhancing material recyclability and maximizing the sustainable use of renewable resources, and also extending product durability and increasing the service intensity of goods and services. And greater the improvement in each of these dimensions and the more is the dimensions, the more eco-efficient is a product or process is. Next is 2D chart. So these are the HV charts, 2D chart, in which the axis in these will be two independent properties. So strength and density don't depend on each other, but if you are forming this type of charts, then you'll be getting these type of bubbles for type of materials. So these are the metals. So these have high density and high strength, and these are the materials which are foams which have low strength as well as low density. So if you are trying to, let's say, maximize strength and minimize density, then you will be forming these type of guidelines for minimum mass design. So here sigma f upon rho, sigma f times 2 upon 3 divided by rho, and root sigma upon rho, these type of guidelines. So you can shift these and you can find out which is your search area. So if your material is falling above this, then you can select those materials for that particular use. So here also you can see for metals and polymers there is yield strength, while in case of ceramics and glasses it is called modulus of rupture, and for elastomers it is tensile tear strength, and for composites it is tensile failure. Next is 3D chart. So performance of a component depends on a combination of various properties. So 3D chart here is of Young's modulus, density and strength. So you will be plotting two properties in particular graph, and here you will be getting 3D type of chart. Next is a case study. So for cantilever design, so first you have to select a cost effective material for a circular cross section cantilever beam loaded at its end, having high stiffness and lightweight. So how to approach this particular problem? So firstly you have to find out what is the free variable. So you can change radius of circular beam cross section, diameter, and also you can change your material choice is free. But what are the constraints? So what you can change, so you have to have maximum deflection and you have to have high beam length. So this is constraint. Then these are the formulas. So for tip deflection, how much deflection from the neutral axis, this is given as delta equals to F L cube upon 3EI. Here F is force, L is length, E is elastic modulus, I is inertia. Okay, so the end force and the tip deflection are thus related as F equals to 3EI upon L cube delta. Here 3EI upon L cube is the equivalent stiffness. And for circular cross section, moment of inertia I can be given as pi d to the power 4 divided by 64. And the mass of beam can be given as density times volume. So volume can be given for circular rod as pi d square L upon 4. Next is, using these two equations, you can write d square as 64 FL cube upon 3E pi sigma. Sigma times delta whole half. So you can write m as pi upon 4 rho L. This again same expression. So you can segregate these various properties. So firstly constants. So pi upon 4 times 8 upon root 3 pi times L to the power 3 by 2. These are geometric parameter which will be such as length, width, thickness. Then you have functional parameter which is force and deflection, and then rho upon under root E. This is your material index. Okay, so in this case you will be trying to have lightweight, so you will be trying to minimize mass. Okay, so mass will be minimized, so you try to maximize performance index, which is inverse of material property index, this particular part. So under root E upon rho will be maximized. Now the maximization of this performance index under root E upon rho, it gives us the solution. Now we require some kind of cutoff value C. So under root E upon rho equals to given as constant C. So taking logarithm on both the sides, we get log E equals to 2 log rho plus 2 log C. Now we get a plot of a log plot of the system, which means log E over log rho. Then depending on this cutoff value C, we actually have a straight line in the log plot. The material which are below this point are not suitable, and the material which are above this point, those materials will become suitable for our application. Okay, so you can see this is the intercept, log E versus log rho, and here these are the materials which are not suitable, these are the suitable materials. So this particular line, below this not suitable, above this search region. So these particular ceramics or metals, these can be used. Okay, so this is the contour E upon E half divided by under root E divided by rho. So CFRP is the best material in terms of performance, but very expensive. So here you can see these particular materials, hence wood is the best choice among the given materials. For steel, E and density is 207.8, and for wood 16.8, and for CFRP it is 200 and 1.6. So the under root E upon rho you are getting is the highest for CFRP, and wood it is little bit lower 5, but its cost is only 450, while for CFRP it is around 2 lakhs dollar per ton. Next case study is for high strength cantilever design. So in this case you have to select the material for a circular cross section cantilever beam loaded at its end, having high strength and light weight. In the previous slides, we found out that the performance index for lightweight and high stiffness beam is under root E upon rho. Here we have free variable, beam diameter and material choice, and constraint as maximum deflection and beam length. Here we have to neglect self weight of the beam. So from bending theory, delta sigma is given as m d upon 2I. Here m is moment of resistance, I is moment of inertia, sigma is bending stress. So bending moment can be given as m equals to Fl. F is this force that is applied, m is the moment. Okay, so this is the length, and this in particular region it will be having tension, and other half it will be having compression. So in second case study we are studying, so for high strength cantilever design, you have to select material for a circular cross section cantilever beam which is loaded at its end, having high strength and light weight. So in previous study we found performance index was under root E upon rho. In this case you have, from bending theory, you have your sigma is equals to md upon 2I. M is moment of resistance, I is moment of inertia, sigma is bending stress, and your bending moment is given as Fl. So on solving further, this sigma can be written as Fl d upon 2 pi t to the power 4 divided by 64. So this is the moment of inertia that is given. Okay, and then you can find out what is the diameter, and mass of the beam is also given as m equals to rho times volume, and volume of a beam, circular beam, is given as pi d square L upon 4. Okay, so you will be just putting this weight. So we want to find out light weight. So m, so here you can put the value of d square. So this will be 32 Fl upon pi sigma. So 2 by 3 will be here because it is square. So you have to segregate again the constants. So constant will be pi by 4 and 32 upon pi to the power 2 by 3. Then you have to segregate geometric parameter, which is length L to the power 5 by 3, functional parameter force F to the power 2 by 3, and then material property index rho upon sigma to the power 2 by 3. So you want to minimize this mass for this beam. So you want to minimize this, then you have to maximize sigma 2 by 3 upon rho. This will be your performance index. Try to maximize performance index. So it can be given as 1 upon material property index. Because for many SEF engineering designs, we can at most take the sigma, particularly if it is linear elastic system, etc. So in this case, sigma can be taken equals to yield stress. So this is for safety. Now for maximization of this performance index, again we have to take some kind of cutoff value. So we put it equals to some constant and taking log on the both side. So you will be getting this equation, and by solving similarly to previous one, we are having intercept. This particular region, it will be not suitable, and above such region will be for the materials which will be providing lightweight. Now here, this particular region, we can see these particular ceramics such as silicon carbide, silicon nitride, and these CFRP. These are the ones which are suitable for this particular application. So the intercept of this inclined line is adjustable to suit our needs, but the slope is fixed for a particular performance index. So our performance index was sigma 2 by 3 divided by rho. Next case study is connecting rods for high performance engines. So a connecting rod is an engine component which transfers motion from the piston to the crankshaft, and together with the crank they form a simple mechanism which converts reciprocating motion into rotating motion. So one of the properties that these connecting rods should have is the fatigue property. So function you have connecting rod, objective is to minimize mass, constraint is length which is specified, and it must not fail by buckling under given force F, and it must not fail by fatigue under given force F, and free variables are material choice and cross sectional area A, B times W. So your width and breadth, these are the ones, and then length. Length is one of the constraints. Now firstly you have to assume shaft has a rectangular cross section, area is BW. Now objective function equation will be again mass equals to rho AL. The fatigue constant requires that the F upon A, the force that you are applying, and the cross section area, it should be lesser than or equal to endurance limit. Endurance limit, which is the stress level below which material will not fail by fatigue for an infinite number of cycles. Material index M1 is rho upon sigma E, and other material index will be in terms of stiffness. So your rho upon E times half. So these two material index M1 and M2, they can be coupled. So M2 equals to alpha pi square upon 12 F upon L square times half times the M1. So here this is the M2 equals to Cc, which is coupling constant, times the M1. So F upon L square is the structural loading coefficient. Now drawing coupling lines for two values of F upon L square are plotted taking alpha equal to 0.8. Now these two lines are drawn, so here the slope is fixed for these particular lines. So F upon L square is 5 MPa. For this particular slope is 0.05 MPa. Okay, so out of these coupling lines, so if you go beyond this, you will be having buckling in your material, and if you go beyond this, then you will be having fatigue in your material. This is the M1 density, which is density divided by endurance limit, and this particular part you have density divided by modulus times half. Okay, so in this particular region you have beryllium and its alloys, which emerges as best choice for all values of coupling constant within this range. When F upon L square is large, around 5 MPa, the best choice for is titanium alloys such as titanium 6Al for vanadium. And when F upon L square is small, around 0.05 MPa, magnesium alloys such as AZ61 offer lighter solutions than aluminum or titanium. And these are the materials which are used for high performance connecting rods: magnesium alloys, titanium alloys, beryllium alloys, and aluminum alloys. In case of beryllium alloys, you have AZ61 and related alloys which offer good all around performance. In titanium alloys, you have Ti 6, as I told earlier, titanium 6 aluminum 4 vanadium is best choice for high F upon L square. And for beryllium alloys, you have the ultimate choice but difficult to process and are very expensive: aluminum alloys, which are cheaper than titanium and magnesium, but they offer lower performance compared to these. Fourth and last case study is design of a probe for scanning probe microscope. So this particular last part, this here, this is the cantilever, this is the tip. So you have to find out material for making these. So this particular scanning probe microscope, it forms images of surfaces using a physical probe which scans the specimen by feeling or touching the surface with a mechanical probe, and the probe is a cantilever beam whose end deflection is detected as a change in the laser beam position at the detector. The bottom surface of the probe has a sharp tip which is a 3 to 6 micrometer tall pyramid with a 15 to 40 nanometer end radius. Deflection corresponds to the surface topography. And here you can see this is the scan direction, and if you have any surface feature, this cantilever tip will be deflecting, and this laser beam will be detecting this deflection using the quadrant photodiode. And this is the map of this surface topography. Now problem statement for this is to select a material for the cantilever beam such that the resonating frequency is maximized. Here objective is to maximization of resonating frequency. Constraint is length and thickness. Free variable is choice of material, and cantilever should have a high resonating frequency, preferably in the range of 30 to 100 kilohertz. And force between the tip and the sample lead to a deflection of the cantilever according to Hooke's law. So this particular beam is the length is L, thickness is T, W is width, and this is tip, and its length is counted from here to here, L tip. Now here firstly we are trying to maximize frequency. So firstly we have angular frequency omega given as kb upon m effective. Kb is your stiffness, which can be given as F upon delta as 3 EI upon L cube, and m effective is effective mass. So end deflection of a cantilever beam can be given as delta equals to FL cube upon 3 EI. I is again inertia, E is elastic modulus, F is force, L is length. Effective mass is given as 33 upon 140 MB. MB is the beam, this cantilever beam's mass. So it is this particular times the beam. Now mass of beam can be given as rho times volume. Volume can be given as all the length times width times this thickness. So this Wt can be written as mb upon rho L. So frequency can be again written as 1 upon 2 pi under root kb upon this linear frequency. Compared to angular frequency, it is written as this one. Then inertia value can be given as Wt cube divided by 12. So F can be finally written with all these equations as this one, and it can be solved as this one. You have T upon L square as the as your parameters, and these are the material property index. So you have to maximize the frequency. So you have to maximize under root E upon rho. So under root E upon rho should be maximized. Now we choose material with a high ratio of E upon rho times half. So slope here will be 45 degree, and in practice the cantilever is typically made of silicon nitride Si3N4, which is cheaper, or diamond with a tip radius of curvature of order of nanometers. So these materials which are falling in search region above this particular line, these are basically ceramics and diamond. Okay, so these are basically used for making this cantilever. Okay, so that's it In case of lecture notes, so I'll be repeating the questions again. In some time I'll be repeating the questions once again. Okay, so first question is select the material for a circular cross section cantilever beam loaded at its end having high strength and lightweight. The options are sigma square upon E rho, under root E upon rho, sigma to the power 2 by 3 upon rho, or sigma to the power 1 by 3 upon rho. So correct answer here will be third one. So here firstly you have to find out for the lightweight. So firstly you have to write the equation for mass. So mass will be density times volume. So volume can be given for circular beam as the pi d square L upon 4. So if you write d in terms of force, length and sigma, so this is 32 FL upon pi sigma times 2 by 3. So you have to segregate these constants: geometric parameter, functional parameter and material property index. So here you will be getting material property index, then you can take reciprocal. 1 upon material property index will be performance index. So you have to maximize this. Sigma times 2 by 3 divided by rho. Okay. So here on this particular graph also you can see these materials are the search region. So out of these you can select material for cantilever beam. Next question is which element is most abundant in the atmosphere? Your options are nitrogen, aluminum, silicon and oxygen. So correct answer here will be nitrogen. In atmosphere you have to you'll be having the gases that are surrounding us. So nitrogen is the highest, 79%. Oxygen is second highest, 19%. Argon is 2%. Carbon dioxide is 0.0. Carbon and carbon dioxide is 0.04%. Okay, so nitrogen is most abundant in the atmosphere and oxygen is the most abundant element in Earth's crust and oceans. Next question is which of the following strategy cannot be used to encounter the shortage of materials? Your options are batch production, continuous type of product, effective utilization of machine, or all of the above. So the correct answer here will be batch production. So batch production is a method of manufacturing where the products are made as a specified groups or amounts within a time frame. A batch can go through a series of steps in a large manufacturing process to make the final desired product. While continuous type of product and effective utilization of machine helps against shortage of materials. Next question is for a constant growth rate of 5%, what will be the doubling time TD? Your options are 13, 14, 15 and 16. So the formula for the growth rate for a constant growth rate R%, the formula for the doubling time can be given as TD equals to ln2 upon growth rate. So it can be approximated as 70 upon R. Okay, and here R is given as 5. So you have to just divide 70 with the 5 and you'll be getting 14 years as the correct answer. Next is which material is less recyclable and eco-friendly? Your options are metal, polymers, ceramic and composites. So correct answer will be polymers. So polymers consist of long chains of carbon and hydrogen atoms, and these molecules form an interatomic type of bonding and is adamant, meaning it is tough for microbes to break the bonds and digest them. Thus a long period is required to decompose them. The polymers with hydrolyzable backbones are susceptible to biodegradation under particular conditions. Next question is which diagram is associated with natural resource recovery? Your options are HB, McKelvey, bubble chart or 2D chart. So correct answer will be McKelvey diagrams. So McKelvey diagram is, or McKelvey box, is a visual representation used to describe a natural resource such as a mineral or fossil fuel based on the geologic certainty of its presence and its economic potential for recovery. The diagram is used to estimate the uncertainty and risk associated with the availability of a natural resource. As a geological assurance of a resource's occurrence decreases, risk increases. As the economic recoverability of a resource decreases, risk also increases. Now, for increasing factor of safety, diameter and thickness is reduced or impurities are added, or diameter and thickness increases or heavy material is used. So correct answer here will be diameter and thickness increases. Okay, so for increasing the factor of safety, the thickness or diameter of a material is increased, leading to the use of more material than required. So though you will be using more material, but it is less likely to material to fail. So for the safety of people that are using that particular machine or structure. Which material is not used for making light high performance connecting rods? Your options are magnesium alloys, titanium alloys, aluminum alloys or zinc alloys. So correct answer will be zinc alloys. So zinc and its alloys are not easy to process and not ductile, and they are not tough, so these are not used for making connecting rods. So these are the four materials for high performance connecting rods: magnesium alloys, titanium alloys, beryllium alloys and aluminum alloys. In magnesium alloys you have AZ61 and related alloys which offer good all around performance. In titanium alloys you have titanium 6 aluminum and 4 vanadium is the best choice for high F upon L square. Beryllium alloys, the ultimate choice, but it is difficult to process and very expensive. Aluminum alloys, it is cheaper than titanium or magnesium, but it is provides lower performance. Which materials are abundantly available? Options are copper, mercury, silver, gold, aluminum, iron and tin, tungsten. So as I told earlier, in earth crust aluminum and iron are abundant compared to other materials which are rare. So copper, silver, tungsten, tin, mercury are rarely available, and iron and aluminum are the mostly widely available materials due to their abundant ores. 10th question is, for a household fan, which of the following mechanical property is most important? So your options are creep resistance, fatigue strength, seawater corrosion resistance and oxidation resistance. So correct answer will be fatigue strength. For a household fan, the service temperature doesn't increase more than the room temperature, while creep and oxidation resistance properties are required when the temperature increases above 200 degrees Celsius. Seawater corrosion is a chemical property and is not required, while fatigue properties are important as cyclic loading is involved in case of household fans. Next question is, which one of the following is not a mechanical property? Your options are creep resistance, density, hardness and fracture toughness. So correct answer will be density. So density is a physical property. It depends on physical nature of a material or element, and which material is most widely available: copper, silver, tungsten, iron. So out of these, iron is the one that has a abundant ore available in earth crust, and copper, silver, tungsten are rarely available materials. And creep resistance, hardness, and fracture toughness are the mechanical properties, and density is a physical property. Next question is HB chart is plotted between. Your options are two independent properties, two dependent properties, stress and strain, or load and displacement. So the correct answer will be two independent properties. So HB charts are plotted between, such as yield strength versus density, or elastic modulus versus yield strength, or other independent properties. Which material is not a good choice for connecting rods? Your options are aluminum alloy, ceramic, titanium alloy, magnesium alloy. So for connecting rods, you require good bending strength as well as good fatigue resistance. So ceramics, they fail catastrophically without any plastic deformation, so they can't be used as connecting rods. Next question is, which material is a good choice for cantilever beam for scanning probe microscope? Your options are elastomer, diamond, lead, and neoprene. So correct option here will be diamond. Silicon nitride and other some of the ceramics also can be used in making cantilever beams, and diamond is one of the highly used material for cantilever beam. Next is material selection in engineering design. So in material selection in engineering design, mechanical design refers to the mechanical components which have mass, they can carry loads and other functionalities such as thermal and electromagnetic requirements, and they must be manufactured. The design refers to the selection of engineering materials based on a set of defined properties. It is a repetitive process. And this is the flow chart. So firstly you have a concept. Firstly you have market need for particular material. You have to design the requirements. Then based on concept you determine function, structure, you seek working principles, you evaluate and select concepts, embodiment, you develop layout, scale and form, model and analyze assemblies, evaluate and select layouts, detail, so you analyze components in detail, optimize performance and cost, and finalize the choice of material and process. And finally you have a product specification and iteration. Selection of properties. So properties can be of various types. Firstly you have price and availability, then you have density, which is physical properties, and other mechanical properties such as modulus, damping, yield strength, tensile strength, hardness, fracture toughness, fatigue strength, thermal fatigue resistance and creep strength. Then you have thermal properties, optical properties, magnetic and electrical properties. Then oxidation, corrosion, friction, abrasion and wear resistance, etc. Then ease of manufacturing and ease of joining, etc. Appearance, texture and feel of material. Then there are various classes of properties affecting product design. First we have economic and environmental. So under these, price and availability, recyclability, sustainability and carbon emission are some of the properties. Then we have mechanical properties, modulus, yield and tensile strength, hardness, fracture toughness, fatigue strength and creep strength and damping. In thermal we have thermal conductivity, specific heat, thermal expansion coefficient. In other general physical we have density. In electrical and magnetic we have resistivity, dielectric constant and magnetic permeability. In environmental interaction we have oxidation, corrosion and wear resistance. In production we have ease of manufacturing, joining and finishing. In aesthetic we have color, texture and feel. Then next is need to determine mechanical properties. What is the need? So firstly to convert raw data into information, into numbers that you understand, and to knowledge, numbers you know how to use. So firstly we will be performing such any tensile test. So data will be captured and based on this data you get various mechanical properties such as fracture strength, UTS, yield strength, elastic modulus, toughness, ductility, etc. And based on those you design your material, and based on that you get, by using less material, by making efficient design, you can get profitable applications. Next is relative prices. So these are various materials and their relative prices. Here steel is considered as the here steel is considered as 100, and these materials starting from platinum, which is 12 million compared to steel, and then diamond, gold, silver, these are some of the expensive materials. Then decreasing you can see ceramics, these have lower prices compared to these. Then further below, some metals with low melting point and with abundance, and some of the polymers which are easy to manufacture are the ones having lower price. And then cement, coal, cast iron, these are the ones having lower price compared to the mild steel. Next is, we have talked about this a lot of times. So this is the abundance chart for various elements in the crust, oceans and atmosphere. So There can be a question asked based on this. So you should remember these particular things. Next is doubling time. So it is the period of time required for a quantity of to double in size or value when the relative growth rate, not the absolute growth rate, is constant. The quantity undergoes exponential growth and it has constant doubling time or period. Example include applied to population growth, inflation, or resource extraction, consumption of goods, compound interest, and the volume of tumors. So for constant growth rate of R%, the formula for the doubling time TD is given by approximated at 70 upon R. Next is resource availability. So current reserve is the known deposits that can be extracted profitably at today's price using today's technology. The resource base can be given as current resource plus known and unknown deposits. So in first one you can see these are the reserves. Then with improved mining technology we can also get other minerals. These are the minimum mineable grade. So the grades which will be having lesser amount of desired element. Then increased prospecting, you can get undiscovered ores as well, and these are the decreasing degree of feasibility and decreasing degree of geological certainty. And these are the energies which is consumed for extracting various elements. So for aluminum metal you require 280 and for copper 140. These require a lot of energy compared to other that are listed here, and some plastics also can get up to 180 and some as low as 85. So and other metals which are made using only melting compared to electrochemical reactions in case of aluminum and copper. Zinc and steel use melt based processes, so they require only 68 and 55 gigajoules per ton of these steel and zinc. Then we have glass, cement, brick, timber, gravel, oil and coal also listed here. Next is availability. So some materials are rarely available. So among these you have copper, silver, tungsten, tin and mercury. And in most widely available materials you have iron and aluminum. Steel consumption is doubling in every 20 years. Aluminum consumption is doubling in every 9 years. Polymer is in every 6 years. So along with the lightness of these materials, that's why light material we are trying to use more. Also the steel that is currently being used is itself in very large amount. So doubling years are higher compared to aluminum and polymer. How to encounter shortage of materials. So firstly, material efficient design can be used. So in this case we use less amount of material. For example, for a good surface property, use cheap substrate and good surface finish. Substitution, substitute rarer materials by the more available ones. For example, copper by aluminum. Recycling, use recyclable material like aluminum. Example of critical mineral used in advanced technologies. So solar panels using arsenic, germanium, indium, tellurium. Battery storage, cobalt, graphite, lithium, manganese. Wind turbines, aluminum, rare earth elements. National defense, chromium, gallium and scandium. Aviation, including niobium, tantalum and vanadium. Next is eco-efficiency. So it merges ecological and economic goals and improving the productivity of energy and material inputs to reduce resource consumption and cut pollution per unit of output. It is a win-win approach which benefits both the bottom line and the environment. And in 1989, Procter and Gamble introduced concentrated detergent powders called ultra detergents, which took up half the volume of traditional detergents. The products cleaned the same amount of clothes but were more convenient for the consumers to handle, used 30% fewer raw materials, required 30% less packaging, and substantially cut the energy needed to transport them to market. 7 dimensions. First is to reduce the material intensity of goods and services. Second is to reduce the energy intensity of goods and services. Then to reduce toxic dispersion of various heavy metals. Enhance material recyclability. So aluminum and some of the polymers, their recyclability needs to be improved further. Maximize sustainable use of renewable resources, extend product durability, and increase the service intensity of goods and services. Greater the improvement in each of these dimensions, and the more the dimensions, the more eco-efficient a product or process will be. Next is 2D chart. So it is the also called Ashby plots or bubble charts. In this case, you have two properties on different axes. So here you can have density and strength. So with materials such as foams and polymers, they will be having less strength as well as less density, so they will fall on this particular corner. And you have metals which have high strength as well as high density. Then you have ceramics, composites bubble, polymers and elastomers, and natural materials. So if you are trying to find say any particular property, so material should be light, or then you will be choosing material falling in this particular region. If you are trying to find strength, then you will be trying to find above this region and these light particular material. And these are the guidelines that will be helping you in selecting these properties. So metals and polymers, you'll be choosing yield strength. In ceramic glasses, you'll be choosing modulus of rupture. In elastomers, tensile tear strength. In composites, tensile failure. Next is 3D chart. These are the performance of a component depending on a combination of various properties. So 3D charts here is of Young's modulus, density and strength. So there will be three charts on combination of two properties. Next is a case study for cantilever design. So here problem statement is to select a cost-effective material for a circular cross-section cantilever beam which is loaded at its end, having high stiffness and lightweight. Solution is, firstly you have to choose what are the free variables. So firstly, radius of circular beam, cross section, and material choice. So constraint can be maximum deflection and beam length. Tip deflection, delta can be FL cube upon 3EI. The end force and the tip deflection are thus related as F equals to 3EI upon L cube delta. Here 3EI upon L cube is the equivalent stiffness. And for circular cross section, moment of inertia can be given as pi d to the power 4 upon 64. Here mass of the beam can be given as density times volume. So rho times pi d square L upon 4. This is the deflection delta. This is the force that is applied. This is the length. Now using equation 1 and equation 2, we can get the expression d square equal to 64 FL cube upon 3e pi delta times half, not times, to the power half. M equals to pi upon 4 rho L times 64 FL cube upon 3e pi delta to the power half. Now M equals to, you have to segregate constant, so pi by 4 times 8 upon under root 3 pi times L multiplied by L to the power 3 by 2 multiplied by under root f upon delta times rho upon under root e. So rho upon under root e is the only ones that are properties. So this is material property index. So as you have to minimize the mass, so you have to maximize this under root e upon rho, which is known as performance index, which is inverse of material property index. Now the maximization of this performance index under root e upon rho gives us the solution. Now we require some kind of a cutoff value c. So under root e upon rho equals to c. Taking logarithm on both sides, we get log e equals to 2 log rho plus 2 log c. We now get a plot of a log-log plot of the system, that means log e over log rho. Then depending on this cutoff value c, we actually have a straight line in the log-log plot, and the material which are below this point are not suitable, and the material which are above this point, those material will become suitable for our application. So this is log rho versus log e plot will be getting an intercept c. CFRP is the best material in terms of performance but very expensive, hence wood is the best option, best choice among the given materials. So here materials are given, so this guideline is here. So above this materials are in search region, those will be the materials that can be used. So material are steel, wood, concrete, aluminum and CFRP. Out of these, CFRP has 8.84 material index and wood has 5, but the cost we can see, wood only $450 per ton, while this is the $2 lakh per ton. Next is high strength cantilever design. In this case, you have to select material for a circular cross section cantilever beam loaded at its end, having high strength and lightweight. In the previous slide, we found out the performance index for lightweight and high stiffness beams as performance index equal to root e upon rho. So free variables include beam diameter and d and material choice. Constant include maximum deflection and beam length. Here neglect the self weight of the beam, and using bending theory we get delta equals to md upon 2I. Bending moment can be given as m equal to fl. So using this, sigma will be, here m is moment of resistance, I is moment of inertia, sigma is bending stress. So using these we will be getting this, and material property index will be rho upon sigma to the power 2 by 3, and you have to take inverse for finding out performance index which to maximize. And because for many safe engineering design we can at most take the sigma p, particularly if it is linear elastic system etc. So sigma p or sig can be taken as yield stress. Now maximization of this performance index gives us the solution. Now we require some kind of a cutoff value c. Okay, so again you can find out the log-log plot and what are the suitable, these are the suitable materials. Here you can change the intercept, but this slope will be same for particular performance index. Next is connecting rod for high performance engines. A connecting rod is an engine component which translates motion from the piston to the crankshaft. Together with the crank, they form a simple mechanism which converts reciprocating motion into rotating motion. Here the function is connecting rod. Objective is to minimize mass, constant is length, must not fail by buckling or must not fail by fatigue under given force. Free variables include material choice, cross sectional area. So width and this breadth, it can be changed and L will be fixed. So here assume shaft has a rectangular cross section, A equal to BW, an objective function equation M can be given as rho AL, and the fatigue constant requires that F upon A should be less than or equals to sigma E. Sigma E will be endurance limit, stress level below which material will not fail by fatigue for an infinite number of cycles. Material index M1 can be given as rho upon sigma E. M2 can be given as sigma rho upon E to the power half. Now these are the two indexes and there will be a coupling constant. Now drawing coupling lines for two values of F upon L square are drawn by taking alpha equal to 0.8. So beryllium and its alloys, they emerges as the best choice for all values of coupling constant within this range. So you have plotted these two lines for different coupling constants 0.05 MPa and 5 MPa, and between these you will be getting beryllium alloys. When an F upon L square is large, 5 MPa, the best choice are titanium alloys such as Ti, 6Al and 4V. When F upon L square is small, 0.05 MPa, magnesium alloys such as Az61 offer lighter solutions than aluminum and titanium. These are the 4 alloys which are used for high performance con rods: magnesium alloys, titanium alloys, beryllium alloys and aluminum alloys. In case of magnesium alloy, Az61 and related alloys offer good all-round performance. Titanium alloy is best choice for high F upon L square. The ultimate choice, beryllium alloy, but difficult to process and very expensive. Aluminum alloys are cheaper than titanium and magnesium alloy but lower performance. Next is design of probe for scanning probe microscope. It forms image of surface using a physical probe that scans the specimen by feeling or touching the surface with a mechanical probe. The probe is a cantilever beam whose end deflection is detected as a change in the laser beam position at the detector. The bottom surface of the probe has a sharp tip which is a 3 to 6 micrometer tall pyramid with a 15 to 40 nanometer end radius. Deflection corresponds to surface topography. Here you can see laser beam is detected with the quadrant photodiode, and this is the tip which will be scanning this surface. The problem statement is you have to select a material for the cantilever beam such that the resonating frequency is maximized. Objective is to maximization of resonating frequency. Constraint, length and thickness. Free variable, choice of material. Cantilever should have a high resonant frequency, preferably in the range of 30 to 100 kHz. Force between the tip and the sample lead to a deflection of the cantilever according to Hooke's law. Now angular frequency can be given as omega n equals to under root kb upon m effective. M effective is effective mass, kb is the stiffness, which is given here with this particular formula. Cantilever beam is deflection is also given. Then effective mass is also given 33 upon 140 times the mass of beam. Now mass of beam is also given rho times volume LWT, and using these all equations the linear frequency can be given 1 upon 2 pi times this angular frequency. So you will be getting these equations and these will be the final segregation. So here you are getting this material index, material property index. So as you know, frequency should be maximized, so this should be maximized. So under root E upon rho should be maximized. So in this particular graph, according to this particular line above these materials, these can be selected. So silicon nitride is one of the material which is chosen, and diamond is one of the material that is chosen for this particular application. So here we choose material with a high ratio of E upon rho times power half, and the slope is taken as 45 degree. And in practice, the cantilever is typically made up of silicon nitride Si3N4, cheaper, or diamond with a tip radius of curvature of order of nanometers. Okay, that's it from my side.